Hello friends. In the last lecture, we have discussed few examples which are based on that comparison test. Now in today's lecture, we will discuss few more examples. And then afterwards, Cauchy's root test to check the convergence of infinite series of real numbers. So friends, see here example number 5. Discuss the convergence of summation n runs from 1 to infinity square root of n plus 1 minus square root of n. So first we'll write here summation un is equal to this given series, that is summation square root of n plus 1 minus square root of n. So it gives here friends un equal to square root of n plus 1 minus square root of n. Generally, if here the right hand side is in numerator or here this expression is in denominator, then in that case, friends, you rationalize the numerator or denominator. So you rationalize this. So after rationalizing, it gives un equal to, there you will get 1 upon square root of n plus 1 plus there you will get square root of n. In numerator here you will get n plus 1 minus n plus 1 plus n minus n gets cancelled. There you will get 1 upon square root of n plus 1 plus square root of n. And then you select here degree of numerator is here 0 because numerator is constant. And if you observe there you will get square root of n as the uh, highest power of or n raised to half as highest power of n in the denominator. So we'll select here that n to be 1 upon square root of n. So and then you take limit of un upon vn as n tends to infinity. You will get it as limit n tends to infinity of square root of n divided by square root of n plus 1 into square root of n. Actually, this square root of n, there you will get 1 upon square root of n. That is, this is value of Vn. So there you will get this square root of n in numerator. Or if you have taken un upon vn, it gives you this expression. And then divide numerator and denominator by square root of n. So there you will get limit n tends to infinity. Square root of n upon square root of n, you will get 1 divided by square root of 1 plus 1 upon n plus there you will get 1. And as n tends to infinity, what happens? This term tends to 0 and there you will get required limit as here 1 upon square root of 1 plus 1 means there you will get 1 upon 1 plus 1, that is 1 by 2. So that obtained limit is here non-zero and finite. So here both series is by using comparison test, limit form of comparison test, both series un and vn behaves alike. But vn is what? Summation vn is summation 1 upon square root of n. And this can be written as n raised to half in the denominator. And if you compare it with 1 upon n raised to p equal to, you will get half. And that value is, you will get it to be less than 1. And that's why by using p series, summation vn is divergent. So if summation vn is divergent, you will get summation un is also what we call it as divergent, means the given series is divergent. Now we will proceed towards the another example, discuss the convergence of summation 8 plus 5 raised to n divided by 3 plus 4 raised to n. So first of all, similar to example number 1 from today's lecture, that is example number 5, maybe first you write let summation un equal to summation 8 plus 5 raised to 8 plus 5 raised to n divided by 3 plus 4 raised to n. And then there you will get un to be 8 plus 5 raised to n divided by 3 plus 4 raised to n. And earlier in the theory part, I have discussed here, you select Vn to be what? 5 raised to n divided by 4 raised to n, that is 5 upon 4 bracket raised to n. And once you know un and vn, you take the limit of un upon vn as n tends to infinity. You will get it as limit n tends to infinity of 8 plus 5 raised to n divided by 3 plus 4 raised to n into there you will get 1 upon vn, means you will get it to be 4 raised to n upon 5 raised to n. And then friends, You divide n numerator and denominator by 4 raised to n into 5 raised to n. So it gives here 4 raised to n gets cancelled. 8 upon 5 raised to n plus there you will get 1. And in the denominator, here you will get 3 upon 4 raised to n. 5 raised to n gets cancelled. And here you will get 4 raised to n into 5 raised to n divided by same quantity. You will get it to be 1. And as n tends to infinity, here this first term in the numerator as well as the first term in the denominator tends to 0, means you will get limit to be 1. And that limit which we have obtained it to be non-zero and finite. So by limit form of comparison test, both series UVN and VN behaves alike. And further, if you observe here this Vn is pi upon 4 bracket raised to n, and this is a geometric series with common ratio is what? 5 by 4, and which is greater than 1. And hence, by using geometric series, summation Vn is what? Divergent. So automatic, what happens? The summation Uvn also, you will get it to be divergent series. Now, in my sense, friends, you will understand here how to solve the examples which are based on the comparison test. Now I will proceed towards the next test, that is Cauchy's root test, to check the convergence of an infinite series of real numbers. So what is that test you see? If summation Uvn is a positive term series such that limit n tends to infinity of Uvn raised to 1 upon n is L, then the series converges if L is less than 1, it diverges if L is greater than 1, and the test fails to give any definite information if you get limit of Uvn raised to 1 upon n is equal to 1. So similar to here, friends, geometric series. Here, sorry friends, if you have calculated the limit of Uvn raised to 1 upon n, if you obtain that limit to be L, and if that L is less than 1, the series Uvn is what we call it as convergent. If L is greater than 1, then the series is divergent, and it fails to give you any definite information if you get L equal to 1. So see the examples which are based on it. Test for the convergence of series whose general term is 1 plus 1 upon square root of n bracket raised to minus n raised to 3 by 2. So first of all, we denote here this nth term as un equal to 1 plus 1 upon square root of n bracket raised to minus n raised to 3 by 2. This quantity we can write in denominator to be like this one. And then what you have to do, you determine the value of L. L is what? L is nothing but limit n tends to infinity of Uvn raised to 1 upon n, and is nothing but equal to, you will get limit n tends to infinity of 1 upon, there you will get this quantity raised to 1 upon n. So here you will get n raised to 3 by 2 means n into n raised to half, means there you will get here power to be square root of n, and then you will get here the required value to be like this one. And we know here this is a standard result. This is standard result. I forgot to write here, friends, limit on both the sides. Here L equal to limit n tends to infinity of Uvn raised to 1 upon n is equal to, on the right hand side also we want limit n tends to infinity of 1 upon 1 plus 1 upon square root of n bracket raised to square root of n. And the value of this numerator 1 remains as it is. Limit of this quantity as n tends to infinity, you will get it as e, and its value you will get it to be less than 1. And if you get L to be less than 1, then by Cauchy's root test, the given series is said to be what we call it as convergent. Now I will proceed towards the another example. Show that the series summation n runs from 1 to infinity, n upon n plus 2 bracket raised to n square is convergent. So friends, you remember, if here un is given in the powers of n, then in that case you use what we call it as a Cauchy's root test. So first we will consider here un equal to, you will get n upon n plus 2 bracket raised to n square. Then you find here limit of un as n tends to infinity, un raised to 1 upon n as n tends to infinity. If we have taken it to be L is equal to, it gives limit n tends to infinity of this quantity raised to 1 upon n. Here 1 n gets cancelled, and then you will get its value to be limit n tends to infinity of n upon n plus 2 bracket raised to n. And then friends, divide n numerator and denominator inside this bracket by n. So it gives limit n tends to infinity of 1 upon 1 plus 2 upon n bracket raised to n. Actually here you will get inside this bracket you will get 1 upon 1 plus 2 upon n whole bracket raised to n. But 1 raised to n is 1. So there you will get 1 plus 2 upon n bracket raised to n. So again to use here this result, here 2 upon n is here. If n by 2 is here, what happens? Means you multiply here in this power by 2, multiply and divide by 2. And we will use here this result for getting the required limit. So I have multiplied here by 2 and here divided by 2. And there you will get limit n tends to infinity of here 1 upon 1 plus 2 upon n bracket raised to n by 2 raised to 2 is there, and that 2 is taken here. And what happens? There you will get its limit, you will get it to be e. So there you will get 1 upon e bracket square, means there 1 upon e square, and which is what again less than 1, because value of e is we know friends, value of e is what 2.71, and if we divide here the number 1 by greater than 1, its value will get it to be less than 1. Again, by using Cauchy's root test, similar to this case, you will get the given series as convergent series. Now we'll proceed towards one more example which is based on it. Test the convergence of the series summation n transform 1 to infinity 3 raised to n upon n raised to 3. So here we will consider un to be as it is, that is the nth term, 3 raised to n upon n raised to 3. And then what we have to do, you find here the limit of un as n tends to infinity, un raised to 1 upon n as n tends to infinity. So is equal to, it gives limit n tends to infinity of 3 raised to n upon n cube bracket raised to 1 upon n. So what happens? This numerator raised to you will get 1 upon n. This denominator raised to you will get 1 upon n. And there you will get what? Numerator you will get 3 and n gets cancelled. And here you will get n raised to 3 divided by n means n raised to 3 upon n. So this 3 is constant, we can take it to be outside. And this can be written as limit n tends to infinity of 1 upon n raised to 1 upon n raised to 3. But friends, you remember here, in earlier one of the example we have discussed this limit. This quantity we can write, this expression we can write it as in square bracket. I have written here limit n tends to infinity 1 upon n raised to 1 upon n bracket raised to 3. So friends, limit of here this quantity, numerator is constant, so further we can write it as 1 upon limit n tends to infinity of n raised to 1 upon n. And if we have calculated that limit you will get it to be 1. So there you will get 3 into 1 raised to 3 is equal to, it gives it to be 3, and which is greater than 1. And if the limit is greater than 1, then by Cauchy's root test, the given series is said to be what we call it as divergent. So friends, in my sense, you will understand here the 2 examples we have discussed on the comparison test, and rest of the 3 examples which are based on what we call it as a Cauchy's root test. So if here power of un exists in the given example, then in that case you use what we call it as a Cauchy's root test. So in my sense, you understand the meaning similar to geometric series. What is the statement? Un given as a series of positive terms, and if we have calculated the limit of un raised to 1 upon n as n tends to infinity, and if that limit is L, then you check whether that L is less than 1, greater than 1, or equal to 1. If here L is less than 1, similar to geometric series, we say the given series is convergent. If L is greater than 1, then in that case, we say the given series is divergent. And if you get L equal to 1, then in that case, we say the given series is, we can't say here whether the given series is convergent or divergent. Its meaning is test fails to give the information about the convergence or divergence of the given series. Now friends, afterwards here only one test from your syllabus is left to finish, and that is nothing but what we call it as a D'Alembert's ratio test. D'Alembert's ratio test. So see today only this statement. If summation un given as a positive term series such that limit n tends to infinity of un plus 1 upon un. Friends, this correction you uh, see uh, or you make that correction in your notes also. This must be un plus 1 upon un plus 1 upon un. If that limit is L, then the series converges if L is less than 1. Similar criteria, similar to that Cauchy's root test is there. Diverges if L is greater than 1, and the test fails if L equal to 1. Here in this case, you take the limit of un plus 1 upon un as n tends to infinity. So instead of this equal to sign, this sign must be plus sign. So you determine here the limit of un plus 1 divided by un as n tends to infinity. And if that limit is a finite, you check whether that obtained value of EL is less than 1, greater than 1, or equal to 1. If you obtained its value to be less than 1, we say the by using D'Alembert's ratio test, we say the given series is convergent. If you get L to be greater than 1, we say the given series is divergent. And if you get L of this limit is equal to 1, then in that case, this test fails to give the information about the convergence of the series of positive terms. So we'll discuss here the examples which are based on in the next year lecture. So today we'll stop here. So we need only the 2 lectures to finish your syllabus. That is nothing but here tomorrow and day after tomorrow you will finish your course. So have a good day friends. We'll stop here.